We saw how can we deal with the categorical attributes where we have categories, right? Because we cannot pass uh, non-numerical values to machine learning models. So we have to first convert each and every attribute to some numerical representation, right? So for that, we will use one-hot encoding to represent categorical attributes in numerical representation, right? So here ocean was our categorical attribute, right? So here we are having several types of categories. So less than 1 hour ocean, near ocean, inland, near bay, right? So these are the uh, categories, right? So we have to convert this attribute in some feature representation, right? Numerical representation. So for that we will use one-hot encoding, right? So in this method, let's say if there are C category, so we will create a vector of size C cross 1, right? So here, as you can see, company name, we can have 3 categories, right? So here we will create a vector of size 3 cross 1, right? Now, if this category is present, so let's say if VW is present, here we will write 1. And for other, we will write 0, 0, right? Yes. And so here we will use positions, right? So for VW, we will use first position. And if this particular category is present, then we will use 1 for that position, right? And we will use 0 for other category, right? So for example, Honda, we will use 0, 0, 1, right? Because here third category is present, right? So this way we can represent categorical attribute to some numerical representation, because here we are using a binary vector, a vector of 0 and 1s, right? So we have converted categorical attribute to binary representation, right? And now machine can understand this binary representation, right? And this encoding is called one-hot encoding because in this binary vector, we will have exactly 1, 1, right? Because all entries are 0 except only one entry, right? So we will have exactly 1, 1 in this one-hot vector. So that's why it is called one-hot encoding, right? Yes. So scikit-learn provides one-hot encoder to convert categorical features uh, into one-hot vectors, right? Okay. So here we can use scikit-learn.preprocessing. We can import one-hot encoder, and we will use one-hot encoder to convert any categorical feature to one-hot encoding, right? Okay. So here, if you use scikit-learn.preprocessing and if you import one-hot encoder, it will give you the one-hot encoding, but it will give us the sparse matrix representation, right? Because now it will represent in compressed form, sparse, uh, compressed sparse raw format. We will get this, right? So here in our training example, in our training data, we have almost roughly 16,000 examples, 16,000 training data. So therefore here the size is 16,512 cross 5, because there are 5 category in our categorical feature, categorical attribute, right? So it will return a sparse matrix of size 16512 cross 5, right? So we can convert this sparse matrix to dense representation, right? We can convert this sparse representation to a dense array, right? So in dense, we will convert uh, values in vector of binary vectors, right? In form of ones and zero, we will represent, right? Yes. So here, as you can see, now we have 16,000, almost 16,000 vectors and the size of each vector is 5 cross 1, right? Because in each vector we are having 5 elements, and there are total 16,512 vectors, right? Okay. Because this OneHotEncoder will return sparse matrix, right? So we have to convert sparse to dense array, right? Yes. So now you may have question why this scikit-learn stores in sparse matrix form, and why not just to store use the dense form? Because as you can see here, we are getting here so many zeros, right? Because in each vector we are only having one single one, right? And all other entries are zeros. So therefore, it will not store these zero, and it will directly store these ones. So for example, let's say if first category is present, then it will for the first input it will simply store the position. So let's say first position we are having one, so it will simply store that particular position. And let's say for the third input we are having one for the second position, then it will store the second position, right? So likewise it will store here in sparse matrix form, right? Okay. Yes. So this part I have already discussed, right? So yes, yes. So if you want to see the categories, we can use dot categories, right? So here also, uh, yes, if because it will return two things, right? So first is the encoding, and the second is the categories, right? So here also, if you want to see the categories, we can uh, we can use uh, dot categories underscore. So it will return the total categories for that categorical attribute, right? Okay. So now we will discuss custom transformer. So here in scikit-learn and in machine learning, we use transformer so that we can write and here we can also write our own transformer to perform custom tasks. So for example, if you want to do cleanup operation, or if you want to combine some attributes, if you want to do some operations, then we can use transformers, right? Okay. So in scikit-learn, pipeline class help us in defining and executing sequence of transformation, right? So here, if we are defining operations, so if you execute that particular that pipeline, it will execute operations in the same order, right? So for example, it will first execute first operation, then second operation, third operation. So I will take one example, and then you can easily see how can we define transformers, and how can we use pipelines so that we can execute sequence of transformation in the right order, right? Okay. So here, here we will create one custom transformer, and here we will follow these steps. So first, we will implement this fit method. Then we will implement transform method, and even what you can use fit underscore transform function, so that you can do these two steps in one method, right? So here we are using fit separately, we are using transform method separately, but in fit underscore transform, we are doing both things in one single method, right? So either we can use fit transform, or we can use transform mixin as a base class to simultaneously do use these both methods, fit and transform method, right? Okay. So here we are creating a custom transformer for combining attributes, right? So I discussed the examples where we combined multiple attributes to create hybrid attributes, right? So for example, rooms per household, populations per household, right? So in our data sets, we are having attributes, and uh, we are using those attributes. We can create custom attributes, right? We can create hybrid attributes, right? So for example, uh, rooms per household we can easily create using rooms attribute and household attributes, right? So this value we can easily get by using rooms and household attributes, right? So room per household means room divided by household, right? So for that, we will create here custom transformer, right? Okay. So here we will use uh, combined attribute adder class, and we will create these additional attributes, right? Rooms per household and population per household. Yes. So here first we are importing base estimator and transform mixin from scikit-learn.base. Here this base estimator uh, is a class from scikit-learn that provides basic functionality for machine learning, right? So, for example, let's say gate parameter or set parameter. So, these basic functionality this base estimator will provide, right? And this transform mixin we are using so that we can use fit and transform method sequentially, right? So, by using this transform mixin, we can use fit and transform method sequentially, right? Okay. And here, these column indices we are defining. So here, room ID, room indices is 3, bedroom indices is 4. So these are the indices that we have in our data set, right? Okay. Yes. So as you can see here, uh, let's say room indices. So this is the uh, room uh, total number of rooms, right? So if you want to get this value, we can get so its position is, let's say, 1 2 3 and 4, right? So its id is 4. So same total number of bedrooms, so uh, we can get this attribute using positions, right? So 0 1 2 3 and 4 and so on, right? So this value we can get using indices 3. This value we can get using indices 4, right? So these are the indices. Yes. So here room index is 3, bedroom index is 4. So we have defined room uh, these column indices, and then here we are defining init function, right? So init function defines optional parameter here, adds bedroom per room, right? So add bedroom per room, this is an optional parameter, right? So by default, its value is true, because here we are writing is equal to true, right? Yes. So this is an optional argument. So if you want to add some optional argument, we can define that argument in init function, right? Okay. And this add bedroom per room is again a hybrid attribute that we are estimating using two attributes, right? Bedrooms divided by uh, total rooms, right? So we will get this value. Okay. this fit function, this fit function method is required for all transformation in scikit-learn, right? So if and we will use this fit function if you want to do any operation, any transformation in scikit-learn, right? And even if it doesn't need to do anything, we have to write this function, fit function, right? Okay. So here in fit function, as you can see, we are returning self, right? Because this function is not doing anything, but still we have to write this function, fit function, right? Okay.
Why
Now
do we
let's
have to write fit function? Sorry, maybe I missed it.
no. So it's the sequence of operations. We will use first fit function, then we will use transform function, right? So we have to use these two methods sequentially, right? But yes, here this fit function is not doing anything, right? But it's not like that. In all cases, it will not do anything, right? Because let's say um, if you are fitting any model, or if you are doing, let's say you are fitting some model, right? So there this function will do something, right? But here in this particular case, this fit function, we are not doing anything, right? Okay.
Can you explain this self again? Like, can you go back to the script again?
Yes, yes. I think I have defined these operation in one of my slides. Yes, yes. So here we will first fit the data to the instances, and then we will use transfer function to transform data to the fitted instances, right? So we have to use first fit function and then the transform function. So first we will fit the data to the instance, and then we will transform data to the fitted instance, right? Yes. So any doubt here in this fit function?
Yep. What is this return self means here?
No, no. So here we are not doing anything. We are just returning self, right? Which means we are not doing anything.
Okay. And the above one is the constructor, right? If I'm not
Yeah,
wrong.
init function. So here, if we have any optional parameters, so we can define here that parameter, right?
Okay.
Yes. So as you can see here, add bedrooms per room is equal to false, which means we don't want this attribute, right? So if we want that attribute, here we will write bedroom per room is equal to true, right? So if this is true, then it will define this one extra attribute, right? Add bedroom per room. But let's say if this condition is false, then it will not create this attribute, right? Okay. Now in transform function, uh, yes, we are calculating rooms per household and population per household. So these two new attributes we are creating using existing attributes, right? So rooms per household, we can get this value by by calculating rooms divided by house, right? Okay. So as you can see here in transform method, new attributes we are calculating. Two new attributes we are calculating. Okay. Now, if this condition is true, add bedrooms per room is equal to true, then we will compute third attribute. But if this condition is false, then we will not compute, we will not calculate this third attribute, right? Okay, so depending upon whether this condition is true or false, we will compute this third attribute. If this condition is true, then we will calculate three attributes. If this condition is false, then we will only compute two attributes, right? Okay, now after computing these three attributes or two attributes, depending upon this condition, whether this condition is true or false, we will return these new attributes that we have computed, right? Any doubt in this code?
I could not understand. What is this add bedrooms per room? I don't
No,
get like
yes,
logically
yes.
also what
Mhm,
it's.
mhm. So add bedrooms per room is a optional argument, you can say,
No,
right?
what exactly that mean? Like one room has multiple rooms? I didn't get that.
No, no, bedrooms divided by number of rooms, right? So let's say if
Oh,
in a district we are having 150 number of rooms, out of which only 50 rooms are the bedrooms, right?
okay.
Because room may be a bedroom or room may not be a bedroom, right? So let's say if 1,000 rooms are there in a district and only 100 are the bedrooms, right?
Okay, and what is this calculation bedrooms per room? Which is x colon bedroom index divided by.
Yes. So here we are using total number of bedroom in a district divided by total number of room in in that same district, right? So bedroom per room is nothing but the bed number of bedrooms divided by number of rooms, right?
Okay.
Because in a district, let's say 100 rooms are there, right? And only 50% of 50% are the bedrooms, right? Okay. So after computing these extra features, we are here concatenating these features and we are returning these concatenated features, right?
One more thing.
Yes.
So this is saying that X is the total training set, right? X, the capital X.
Yes. Yes.
So
Capital.
colon bedroom index means it is from 0 to bedroom index is 4. So the first 4 elements in that training set divided by room index is 3. So how was that calculation? Can you just explain some with some example? I
No, no.
didn't
So
get it.
X is a tabular data, right? X is a tabular data, or you can say X is a variable holding our data sets, right? So where our data set in the form of tables, right? Rows and columns. So we are filtering bedroom column divided by row column, right? So and so for example, let's say yes, let's say you are dividing total number of rooms uh, divided by yes. Yes. So let's say you are dividing this 534 divided by 2622. So for that, what you will do, you will first fetch this particular value 534, then you will fetch this value 2622, and then you will do this division operations, right? So total bedrooms divided by total rooms. So here we will first select this particular column, then we will select total room column, and then we will compute that attribute, right?
So
So
what
now,
sorry, Dr. Praveen, what will we get by dividing this? And like, what are we doing in this transform thing? I'm maybe lost.
no. So here we are computing extra attributes using existing attributes, right?
Okay.
Yes. So we are
And
using two or more than two attributes to make extra attributes, extra features, right?
okay. And why is that required?
No. Here in that particular code, I'm just explaining if you want to do some let's say if you want to define some custom transformation, then how can we do that, right?
Okay.
So we have to define fit method, we have to define transform method, and then we can define any extra facility. Let's say if we want to do some coding, then how can we do that, right? So we have to define first fit function, then transform function, right?
Okay.
Why do we need a custom transformer here? Why can't we do just like this calculation? We can do it on the data set, right? Why do we need that a custom transformer?
No. So yes, so we will not use but here we want to create these two new extra attributes. So that's why for that we are defining this class custom attribute editor.
That's the same question. So this extra
Mhm.
attribute I can add to this data frame without this combined attribute, this transform, fit, and all these things, right? I can just calculate this simple calculation and I can get the values and I can put it into data frame. Why we need this whole ScikitLearn transformer thing, custom transformer thing?
No. So here, this simple thing you can do. So, for example, let's say what you can do, you can convert this tabular data in some NumPy array, and then you can use array operations, and then you can simply add that particular columns to our data set, right? So that we can also do. But here, don't think we are only using this fit and transform to do these simple things, right? So here I've taken this simple example so that you can understand better. But the purpose is not just restricted to creating new attributes, because here, let's say you are building a machine learning model, right? So for that we are having data. Now you want to fit a machine learning model using that data. So for that model fitting part, we will use these functions. We will first fit uh, a model to the given data, and then we will apply some transformation. So there also we will use these operations, fit and transform, right?
So if it is a complex transformation, then this will help.
Yes.
Okay.
But the same operation you can also do using NumPy array, right? So what you can do, you can simply fetch these two columns. You can use the division operation, and that new column you can add to the to our existing data set. So that the same thing you can also do using other operations, right? So you can use NumPy array to get the same result, right? Any other doubt?
We have not used base estimator and transform mix in
Yes.
that we passed into this function. So what is the use of importing that you from sklearn we imported these base estimator and transform mix in. So where are we using this?
Yes. So, let's say if you want to use fit and transform methods in one method, let's say uh, you want to. So here in this particular example, we are using a fit method and transform method separately, right? But using this transform mixin, we can write a joint method fit underscore transform to do these fit and transform simultaneously, right? So that example I'm coming, right? So in my slide I have one
Okay.
examples where we will use this, right? But yes, in this particular example we are not using it, right? Okay. Yes. So using this combined attribute adder class, we can now add extra attributes to our data set, right? And this is the code as you can see here, we have added 2 extra attributes, right? Room per household and population per household. And if you display this our data set, then as you can see here, now we have added 2 extra attributes: rooms per household and population per household, right? Because here this optional argument is false. But here, if you write adds bedroom per room is equal to true, then it will add 3 extra attributes, right? Okay. Now, let's say sometimes we also need data pre-processing. In data pre-processing, what we generally do, we will we will apply some transformation to our data so that we can train machine learning model better in a better way, right? So here, the first transformation is feature scaling. So sometimes we also do feature scaling. In feature scaling, what we do generally, we scale features and we try to make all attribute to the same scale, right? So here in our example, as you can see, we are having rooms, and rooms, number of rooms can vary from 6 to roughly 40,000, right? While the median income attribute only range from 0 to 15, right? So here for median income, the range is from 0 to 15, and for the total number of room ranges up to 40,000, right? So this may create a problem when we build a machine learning model. So what we generally do, we first apply feature scaling as a pre-processing step, right? Okay, now how can we apply feature pre-processing? For that, we have different methods. But here, the goal is how can we make this medium income and the total number of room on the same scale, right? For that, we will use feature scaling. So this feature scaling we can only apply if we have numerical attributes, right? And if attributes having different scales, then we use feature scaling as a pre-processing steps, right? Okay. So here we will see 2 methods to do feature scaling. First method is the min-max scaling, and the second method is the standardization, right? Okay. So in min-max scaling is also called normalization, and here we normalize values in such a way, after normalization we will have values from 0 to 1. So in this range we will have value 0 to 1, right, after normalization. So here, let's say this is the actual data that we have, and after doing this min-max scaling, this is the normalized data, and as you can see, this normalized data is in the range of 0 to 1, right? Now how can we do this this min-max scaling? This is the formula to do the min-max scaling: original value minus minimum value divided by maximum minus minimum value. So here the maximum value is 100, minimum value is minus 100. So for example, let's say if we are scaling this particular value, we will use here original value is 0 minus minimum value is minus 100 divided by maximum value is 100 minus minimum value is minus 100, right? So after doing this calculation, you will get 0.4 value, right? Yes. So if we do feature scaling, it will help in the model optimization part, right? Because if we are not doing scaling, if our features, let's say one feature is on other scale, another feature is on different scale, then we will face difficulties in optimizing models, right? But if we have used, let's say, feature scaling, and all our features are on the same scale, then it will help optimization process, right? We will get our model, we will get our solution quickly, right? So this is why we generally do the feature scaling part, right? Or we pre-process our data, right? Because pre-processing helps in learning a better model, right? Learning a better machine learning model, right? Okay. So if we want to do this feature scaling, minimax scaling, we can use pandas. So here we are importing pandas as PD, and we are using pd.series, and here we will write the values that we want to scale, right? That we want to perform minimax scaling, right? Okay. So this S1 is first attribute, 1, 2, 3, 4, 5, 6. S2 is another attribute, 10, 9, 8, 7, 6, 5. And we want to apply minimax scaling over attribute S1 and S2, right? Yes. So to apply minimax scaling, we will use minimax scaling. We will first import minimax scaling, and then we will pass our data set. So here df is the variable that contains this data set, and in this particular data set we are having two attributes. S1 is the first attribute, S2 is the second attribute, or in this particular data set we are having total 6 points, right? So 0, 1, 2, 3, 4, 5, 6. So we are having total 6 data points, and two features are there, or two attributes are there, right? So S1 is the first feature or first attribute, S2 is the second attribute, right? Okay. So after applying minimax scaling, as you can see, now S1 features having values in ranging from 0 to 1, S2 also having values from 0 to 1, right? So as you can see here, this S2 value is 10, 9, 8, right? But S1 lies from 1 to 6, and S2 lies from 5 to 10, right? So here S1 feature are, as you can see, values are lying from 1 to 5, 1 to 6. S2 feature values are lying from 5 to 10, right? But after doing this minimax scaling, now both S1 and S2 values are from 0 to 1, right? Okay, so any doubt in minimax scaling? Okay. Next method is the standardization. So again in standardization, we do the feature scaling, right? So in machine learning, we handle several types of data. So for example, we can build a machine learning model that takes audio signals as an input or images as an input, right? And images can have multiple dimensions, right? So for example, RGB image can have a red channel, green channel, and a blue channel, right? So we can use audio data, we can use image data, we can use video data to train a machine learning model, right? So if we are using these types of data as an input, then we will use standardization as a feature scaling technique. And now what exactly we will do in standardization? We will use mean and sigma to standardize the value, right? So here the formula is simple: x minus mu divided by sigma. So x is the old value minus mu is the mean value divided by the sigma is the standard deviation, right? So this method is called the standardization, right? X minus mean divided by sigma, right? So here we are using standard normal function, and by standardizing, and here we are standardizing x value to x prime, right? So this
But
old
then,
value,
Dr.
yes,
Praveen,
yes, yes.
sorry to interrupt, but
Mhm.
then why do we need to standardize? Mean this way we are just manipulating, changing the original values, right?
Mhm.
Why
Yes, yes,
is that
good.
required? Instead of that, whatever
Mhm.
the like models we are trying to create, that should be using the original data.
Mhm. Okay, okay. So here, if we are applying any scaling, any feature scaling to our training data, the same method we will apply to our to our test data, right? So it's not like that we are changing our data, we are changing the value, right? Yes, since we are pre-processing, we are using this standardization method, so it will change the value that we originally have in our data set, but we also apply the same standardization method to our test data, right? So once we use any machine learning model, we first convert test data or training data using the same method, right? So for example, let's say if we are using, let's say, this particular formula, x minus mu divided by sigma, to pre-process our training data, the same formula we will use for the test data, right? So it will not create any problem, right? But let's say if you are using standardization to the training data, but you are not using the same standardization to the test data, then model will give you the wrong result, right? And the question is why we are doing this standardization, so that we can learn a better model. It will help in optimization, right? Otherwise, model will follow a optimization will follow a zigzag path, and it will require huge number of iteration to get the optimal value, right? Because we are having different scale values for different features, right? So this is why we are scaling each and every features, so that we can have values in the same range, right? Any other doubt?
But is there any use case do you have where we can see, how these things fit? Or maybe the example what you're taking, previous.
Mhm. No, but feature scaling, or we do as a pre-processing step in training all machine learning models, right? So it's
So
yes.
it's a mandatory step, the
Yes,
point you are
yes,
making.
yes, sir. It's a mandatory step. Otherwise, the optimization method will take huge number of steps for convergence, right? So it's not like that. You can use the actual values. You can use the actual values, but let's say then you have to use some optimizer, right? So, for example, in later sessions, I will discuss one method for optimization, gradient descent, right? So gradient descent is the iterative methods that optimize any machine learning model iteratively, right? So for example, let's say it can converge, it will give you the optimal solution, let's say after 100 iterations, right? But let's say if you are not using feature scaling, you may get the solutions, let's say after 1000 steps. So if you are not doing these types of pre-processing, the same method will take more and more steps to get you the solution, right?
So we have to apply these feature scaling on all attributes, or we have to select, or it's kind of trial and error, or
No, all
by
attributes.
experience on
Yes,
all
yes,
attributes.
all
And
attributes,
then
but yes.
like standardization or other scaling technique, like how do we choose that?
Yes. So it depends on what type of features we are using, and uh, what is our model, right? So for example, let's say if we want values to be in 0 and 1 range, then we will use min-max scaling, right? So sometimes for machine learning model, it is the requirement that values has to be in 0 and 1 range, then we can use min-max. Otherwise, let's say for audio data, for image data, we use standardization, right?
We have different libraries for minimum and maximum scaling because in the slide you showed it's using from MLXN, and there is also one present in scikit-learn.
Yeah, so yes, so you can use any library, but the formula is same, right?
Okay.
Yes. So here in standardization, what exactly we are doing? If we are doing x minus mu divided by sigma, so we are here calculating how many standard deviation is the value away from mean. So this particular value we are calculating because we are using x minus mu divided by sigma. So since we are dividing this value by sigma, so it will calculate how many standard deviation is the value away from mean, right? So here, let's say we have here I have taken one example. Let's say we are calculating, we are standardizing these values, these two values, right? 1800 and 24. So for 1800, let's say the normal standard normal distribution, we are using two standard normal distribution, one for uh, uh, first feature and other for the second feature, right? So now let's say value for the first feature is 1800, right? And mean value is 1500 and standard deviation is 300. And for the other feature, mean value is 21 and standard deviation is 5, right? So after applying standardization, as you can see, both feature values are on the same scale, right? So here we are getting 1 and here we are getting 0.6. So this one is what telling this value 1, what it signifies, it is telling this particular feature value 1800 is one standard deviation away from its mean, right? And this GIM 24 value is 0.6 standard deviation away from its mean, right? So this for the second feature we are using another standard normal, and for this first feature we are using some other standard normal function, right? So for that standard normal function, 1500 is the mean and 300 is the standard deviation. And for the other standard normal function um, distribution, 21 is the mean and 5 is the standard deviation, right? Okay. So using this formula, we can do standardization and we can do feature scaling, right? Yes. So after applying this formula x minus mu divided by sigma, we have scaled all features on the same scale, so that now we will have zero mean and unit variance, right? Okay. So after applying this this standardization, we can say that now we will have zero mean and unit variance, right? Okay, so scikit-learn provide standard scalar class for standardization, right? So we will use standard scalar class to do standardization, right? Okay, so min-max scaling convert features in 0 to 1 range, but standardization we will not have any upper bound. So for example, in min-max feature scaling, the lower bound is 0, upper bound is 1. But in standardization, uh, there is no upper bound, right? Because we are using this particular formula, x minus mu divided by sigma. So upper bound can be any number depending upon this value x, mu, and sigma, right? Okay. So let's say if we are training a machine learning model where the requirement is the values has to be in this range, then we will use min-max scaling. And if we are dealing with audio data, video data, or let's say image data, then we generally use standardization as a feature scaling technique, right? Okay, so let's take a 5-minute break and then I will start transformation pipeline. Okay, let's start. Am I audible?
Yes.
Yes. Yes. Transformation pipeline. So here, in sometimes what we can do, we can execute several transformation steps, and we can combine these transformation steps to make a single pipeline, right? And for that, we will use scikit-learn pipeline class, right? So, for example, let's say if we want to do these three operations, we want to, let's say, uh, impute some missing values, right? Because missing values can be there in our data set. So let's say we want to impute, we want to fill out that those missing values, uh, and then we want to, let's say, add some new attributes to our data set. So for example, we want to add two new extra attributes to our data set, and let's say after adding extra attributes, we want to do feature scaling, right? So we can do all these three steps, and we can create a pipeline, and using that pipeline, we can do these three steps, right? So pipeline, and for that, we will use scikit-learn pipeline class, right? Okay. So if we want to execute these three steps, right? So we want to handle, we want to impute missing values. And let's say for missing values, we are using median age strategy, right? So we will use simple imputer class to, to, to impute missing values. And this combined attribute adder class I discussed in today's session, right? So using that custom class, we can add extra attributes to our data set. And this feature scaling, for feature scaling, let's say if you want to do standard, if you want to use standardization method, right? So for that, we will use standard scaler class, right? Okay, so we will first import pipeline from package scikit-learn.pipeline, and for standard scale, we will use scikit-learn.preprocessing. We will import standard scaler to do feature scaling, right? Okay, so here we will create a pipeline. So we will write this num underscore pipeline is equal to pipeline. So this is the variable, right? Num underscore pipeline is the variable. And here in using this pipeline, we will create a pipeline. Uh, and let's say we are defining these three steps. So it will first perform this first step, impute step, right? So it will fill out missing values. Then it will add extra attributes to our data set. And then in the third step, it will do the scaling part, feature scaling part, right? And let's say if here we want to use median age strategy, so we will write here median, right? And after defining this pipeline, we will use uh, num underscore pipeline, which is a variable, right? Dot fit transform function, and we will pass our data set. So this housing underscore num is a variable that is holding our data set, right? So now over our data set, it will perform these three steps. It will first fill out missing values, then it will add extra attributes, then it will do the feature scaling, right? So any doubt in this code? And yes, here we are using fit underscore transform function. So using one method, we can do fit and transform simultaneously, right? Or what you can do, you can first call fit function, and then you can call transfer function, or directly you can call fit underscore transform, right? Okay. So this pipeline constructor takes a list of name estimator pair defining a sequence of steps, right? So here this imputer is the name. So here you can use any name, right? So in fact you can write here IMPTR, or you can use any name here, right? And this simple imputer is a estimator, right? So this is the name of that estimator, right? So is here we have defined, right? So attribute adder, here you can write any name, and this combined adder we have defined, right? We have defined custom class for that, right? Standard scaler we have imported from scikit-learn pre-processing. So here we are using this standard scaler to do the feature scaling part, right? Yes. So when we use fit underscore transfer function, it will apply fit transfer function to each and every steps that we have defined here, right? So it will first apply fit transfer function to simple imputer, right, class. Then it will apply fit transfer function to combined attribute adder class. Then it will apply fit transfer function to standard scalar class, right? So when we write here dot fit underscore transform, it will apply fit transfer function to each and every steps one by one, right? So first it will apply fit transfer function to simple imputer class, then it will apply fit transform to combine attribute adder class, then in the last it will apply fit transfer function to standard scalar class, right? Yeah. Okay. So actually, we can skip this slide because now scikit-learn doesn't have this problem. But in earlier version of scikit-learn, we have this problem that we cannot use uh, pandas data frame as input, and what we can do in earlier version of scikit-learn packages, that we need to first convert the data frame to NumPy array, and then scikit-learn can understand only the NumPy array. But nowadays they have fixed this problem, and we can directly use data frame as an input, right? But in old versions of scikit-learn, we need to first convert data frames to NumPy array, and then scikit-learn can handle that data, right? Okay, so here this data frame selector is nothing but a class using which we are converting data frames or pandas data frame to NumPy array, right? So again, as you can see here, we are defining fit function and transform function, and in this transfer fit function, we are not doing anything. In transfer function, we are simply returning data frame to NumPy array, right? Because yes. Any doubt? Okay. So what this code will do, it will convert data frame to NumPy array, right? Okay. So if you are using old version of scikit-learn, then you can write this this line data frame selector. Or if you are using the recent version of scikit-learn, then you can skip this first line, right? Okay, so in this pipeline, what exactly we are doing? We are simply first converting to NumPy array data, and then we are imputing missing values, and then we are adding attributes, extra attributes to our data set, and then in the last we are using feature scaling, right? Okay, so now we are having two types of attributes in our data set. First category is where we are having numerical values, and the other category is where we are having categorical features, right? So here in this particular variable housing underscore num, we are having feature values or the values for numerical attributes, right? Similarly, since this Ocean proximity is a categorical attribute, so we are processing this attribute separately, right? So housing num is a variable that contain the complete data sets where we are having only numerical attributes, right? And this categorical attribute is again a variable that is holding data for categorical attributes, right? So in our data set, we only have one categorical attribute, ocean proximity. So you can think that housing num is a variable that contains the complete data except this ocean proximity attribute, right? And this categorical attribute contains only one column, ocean proximity column, right? Because ocean proximity is a categorical attribute, right? So if we are having numerical attribute, then we can use this particular pipeline. We can fill out missing values. We can add extra attribute. We can do the feature scaling, right? But let's say if we are having categorical feature, then we need to first convert categorical feature to a numerical representation, and for that we can use OneHotEncoding, right? So yes.
Sorry. So what is the definition of, for any attribute to be qualified as a categorically?
Yes. So categorically means we are having several types of category for that particular attribute, right? And numerical attributes means where we are having numerical values. So for example, real values, or let's say binary values, or let's say the values can be discrete or can be contiguous. So for example, height of a person. So height of person is a real value, right? Or let's say weight again a real valued attribute, right? And let's say here this particular ocean proximity, we are having several types of categories for that particular attribute. That, and or in other word, in simple terms, what you can think, for categorical attributes, we don't have numerical values. We are having some categories, right?
Okay.
So for example, let's say you may have rating attribute. So rating can be good, bad, right? So there can be different categories of that particular attribute, right? Okay. So since ocean proximity is a categorical attribute, so therefore we need to first convert this attribute to some numerical representation, and for that we will use OneHotEncoding, right? Okay. Now we are having two pipelines, one pipeline for numerical attributes and other pipeline for the categorical attribute, right? Okay. So for numerical attributes, we are using feature scaling, but for categorical features, we are not using feature scaling, right? Because now we don't need feature scaling, right? Because this attribute, this ocean proximity attributes does not contain any numerical values, right? And all these attributes having numerical values, so that's why we are normalizing it, right? We are using standard scalar class to normalize our data, right? Okay, so this is the pipeline for numerical attributes, and this is the pipeline for categorical attributes. Now we will use feature union class to combine these two pipelines, right? Because we are having one pipeline for numerical attribute, other pipeline for categorical attribute, right? So this is the pipeline for numerical attribute, and this is the pipeline for categorical attribute, right? So we are using feature union class. So we will import feature union from scikitlearn.pipeline, and then we will use feature union to combine these two pipelines, right? Yes. Yes. So what this feature union class will do, it will execute these two pipelines, right? Yes. So each sub pipeline start with a select transformer, and it simply transform the data by selecting desired attributes, right? Because here in first pipeline we are only using numerical attribute. In the other pipeline we are only using the categorical attribute, right? So it will drop other attributes, because in first pipeline we only need numerical attributes. For other pipeline, second pipeline, we only need categorical attribute, right? Yes. So we can run this complete pipeline, right? Because we have defined full underscore pipeline is equal to feature union of these two pipelines, right? One pipeline for the numerical attribute, other pipeline for the categorical attribute. Now, if you want to execute this full pipeline, complete pipeline, which is nothing but a union of these two pipelines, you can write dot fit underscore transform function, right? So you can write full pipe underscore pipeline dot fit underscore transform function, and you will pass here our data set. So now housing is a data set, is a variable that contain complete data, right? So now your data is prepared, and you can use this data to train any machine learning model, right? Okay, so up to this point, we are preparing our data so that we can use the data to train any machine learning model, right? Okay, so we have used several steps. So for example, we have divided data into two parts: training part and test part. So training part we will use to train our model, right? Now we have applied several kinds of pre-processing to our data set. So for example, if we have any missing values, we can fill out that missing values, we can clean our data, and sometimes we also use outlier detection methods to remove noise present in our data, to remove outliers present in our data. So data cleaning we generally do, right? And then we do feature scaling so that we can optimize our model in a better way, right? So after doing all these steps, now our data is ready to train any machine learning model, right? So we will use this data to train machine learning model, right? Okay, so we will use different models, and we will use cross validation to select, to pick the best model, right? So we have our data, our process data. We will use this process data to train multiple models, right? Now we can use different machine learning models, and we will use this data to train multiple models, and we will choose the model that maximizes our accuracy, our performance, right? Yes, so this slide I have already discussed, right? We have created training set, test set, we have cleaned up our data, prepared our data. Now we will use process data to train a machine learning model, right? Yes. So depending upon our problem and our data, we can train multiple models, and we will select the best model. So here, for the same problem, for the same task, we can use different models, right? So let's say you want to, let's say you are solving a linear regression problem, or let's say you are solving a, yes, let's say you are solving a linear classification problem. Now, to solve a linear classification problem, you can use several models. So for example, you can use support vector machine. Support vector machine again a machine learning technique using which we can learn a linear model, right? So you can use support vector machine. You can use let's say nearest neighbor. You can use learning with prototype. So you can use deep learning, right? Deep learning model. You can use neural network. So we can have multiple different model for the same task, for the same problem, right? So what we can do, we can simply try all these models, and we will pick the model that maximizing our performance, right? So now here one point you can note here, it's not like that uh, for all problems only one particular model always perform the best, right? So it may happen that for your data set, for your problem, one model is doing better than other class of model. So for example, support vector machine, if you use support vector machine, you may get the better model, right? But for other problem, let's say uh, learning with prototype, or let's say the random forest is doing the is giving us the better model, right? So depending upon our problem, our data set, we may get uh, we choose the best model. But before executing any model, we cannot say anything, right? So it's not like that a priori we know this is the best model, right? We have to train each and every model, and after training, we can only say that this is the best model for this particular problem, right?
So Dr. Praveen, so once
Yes.
we suppose we train this model and then we see okay this model is fine or not fine, but then should we also revisit how we have prepared the data? Because suppose with a certain model we are not getting the results, but then that might be because of the way we have prepared our data, the original data, right? Like if we have used standardization, but instead of that we could have used something else.
Yes, yes.
So do we have to go back? So it's more like trial and error kind of thing, or
Yes,
with
yes. So
obviously with experience we will know, but
yes. So it depends on, as you said, experience, but sometimes we also do. So let's say if you are using some particular model and that model is not giving the optimal result, then it may be the problem with the feature scaling, or let's say you are not using the correct feature, or sometimes what we do, we also do the feature selection. So let's say if originally we are having 100 features and only 10 features are relevant, so what we can do, we can simply discard 90 features and can only proceed with the 10 features, right? So feature selection is a pre-processing step that we generally do. So yes, you are right. So
okay.
sometimes we also go back and we do other pre-processing so that we can get the better result, right? And yes, how can we check the best model? So for that, we will use a cross validation method that I will discuss. I think in the next session I will discuss, right? So in cross validation, what we exactly do, we divide data set into three part: training part, test part, and the validation part. And we will use validation data to decide the best model, right? Because we cannot use the test data, right? Test data we will use as a proxy for future data. So model selection we cannot, for model selection we cannot use the test data, right? Test data we will only use one time, right? So model selection, for the model selection, for picking the best model, we will only use the validation data and not the test data, right? Yeah. So now let's understand overfitting and underfitting before training a machine learning model, because in machine learning model, we generally face these two problems frequently: overfitting problem and underfitting problem. So we need to fix these overfitting, underfitting problem if we have these problems in our model, right? Yes. So machine learning machines can also fall in the into the trap of overgeneralization. So, for example, so in overfitting is a condition where we are getting our model is performing very well on the training data, but model is performing poorly on the test data, or you can say that training time model is giving very good accuracy. So let's say 99% accuracy we are having, or let's say almost 100% accuracy we are having when we are training a model, or when we are calculating accuracy using training data, right? But for the future times, model performs very poorly. So let's say test time or future time model is only giving 30% accuracy or 40% accuracy, then we can conclude that our model is suffering from overfitting problem, right? So in case of overfitting, training accuracies are high, training performance uh, are high, but at the same time test performance is very poor, right? Or you can say that model does not generalize well on unknown data. So here unknown data means the test data, or the future data, right? Okay. So when does overfitting occurs? So overfitting occurs when a machine learning model capture noise present in the data, right? So let's say you are having 1,000 feature in your data set, right? And only 10 features are relevant, right? So 990 features are not relevant and only 10 features are relevant. So if you use all features, all 1,000 features, then you may suffer overfitting problem. You may suffer from overfitting problem. So I'm not saying 100% you will get this problem. You may or may not get, but you may get overfitting problem because you are using extra features. You are using spurious features, right? You are using redundant or unnecessary features. So that features may easily confuse our machine learning model, right? So now how can we solve that problem? We can use feature selection techniques. We can select only relevant features and train our machine learning model only using that relevant features, and we can fix that overfitting problem, right? So overfitting, because if you use all features, then model will learn each and every pattern present in the data, right? But for the task that you are solving, only some patterns are relevant, right? If you try to learn all patterns, then uh, machine learning model may get confused very easily, right? Okay. So overfitting occurs when model or algorithm fit uh, the data too well, or what you can say, it fit the noise present in the data. So this is why in case of overfitting we are getting very good training accuracy. Model performs very well on the training data because it has memorized everything. It has memorized every pattern present in the training data. So that's why we are getting here very high performance on training data, right? Or sometimes, let's say, if we are using a highly complicated model, then also overfitting can be there, right? Because using highly complicated model, you can learn highly complicated patterns, right? If model is simple, the simple model can only learn simple patterns. So for example, linear model. So linear model is a simple model, and using linear model, you can only learn a linear pattern, right? If you want to capture non-linear pattern, then we have to use non-linear model. So non-linear model is a complicated model than as compared to linear model, right? So if we are learning a highly complicated model, that highly complicated model can learn highly complicated patterns. So that may also result in uh, overfitting problem, right? So there can be several regions for overfitting. And how can we check overfitting? If we want to check overfitting, we can simply check training accuracy and the test accuracy. If training accuracy is high, but at the same time test accuracy or validation accuracy is very poor, then we can say that model is suffering from overfitting problem, right? Now there can be several regions. So depending upon let's say if model capturing noise, or let's say you are using a highly complicated model, or um, let's say um, feature is the problem, feature is creating the problem. So accordingly you will prevent overfitting, right? So let's say if highly complicated model is the problem, or is the cause of overfitting, then we will use simple model, or we will use regularization to make model simpler, to reduce the number of parameters, because when we reduce the number of parameters in a model becomes simpler, right? So we can use this as a step to prevent overfitting. Or let's say if the feature is the cause of overfitting, then we can use feature selections, right, to prevent overfitting. Or let's say if we have the noisy data, then what we can do, we can use some pre-processing techniques to filter out that noise, right? So depending upon what is the cause of what is the region of overfitting, we will follow certain steps to prevent overfitting, right? Okay, so now let's
Dr.
take
Praveen,
yes.
1 second. So you said about regularization. So
Mhm.
what exactly is regularization? What we did for feature scaling and all that doesn't come inside the regularization, right? What do you mean by
No,
regularization?
yes,
Will that
yes,
be covered in
yes,
future?
yes. So yes, yes. So that will be
Okay.
covered. And here, what I mean by regularization, I mean model regularization. So feature scaling means we are regularizing data. And now to prevent overfitting, we will regularize our model parameters, right? Not the data. So data we have already uh, scaled. So using feature scaling, we have already done the scaling part, right? I think one question is there. Yes. So outlier. Yes. So there exist several methods to detect outliers. So if we have outliers in our data, what we can do, we can remove outliers, and then after removing outliers from our data, we can train machine learning models, right? Because if we have the outliers in our data, model may try to fit those outlier points, right? Which means model is now learning unnecessary patterns present in the data. So that may result in overfitting problem, right? So outlier, so there can be several causes of uh, overfitting, right? So we need to first identify what is the reason for overfitting, and then accordingly we will take certain steps, right? So model regularization is one method of preventing overfitting, right? Now in regularization we have several methods, right? So for example, we can do L1 regularization, we can do L2 regularization, we can do L0 regularization. So there are several types of regularization that we can do using we can do to prevent the overfitting problem, right? So regularization is one method. Other method is early stopping. So what we can do, let's say if you are training your model, let's say 100 epochs. So to prevent overfitting, what we can do, we can stop early. So we can stop, let's say after 80 iteration, we can stop, right? Because let's say if you are overtraining your model, which means uh, now model is trying to capture more and more pattern present in the data, right? So sometimes what we can we generally do, we stop early, right? So that model can only learn the relevant features, right? Because initial in initial few steps, model try to learn uh, more relevant patterns, right? And as you train your model more and more, it will try to capture noise present in the data, right? So that may sometimes end up in overfitting problem. So I'm not saying always you will get the overfitting problem. Sometimes you may get the overfitting problem, right? So one technique is early stopping, right? So using that we can prevent overfitting, right? Yes. Yes. So here is one example. So let's say, as you can see, we are predicting price of house using house size, right? So house size we know, and we want to predict its price, right? And these are the data points that we are given in our training data, right? So in our training data, we have these data points, right? Cross points we are having. Now, as you can see, this price to house size relationship is non-linear, right? Price to house size relationship is non-linear. So if you use any linear model will not be able to fit this data, right? So here we are learning a line, we are learning a linear model. So using this linear model, we cannot model non-linear data, right? Because the data is non-linear in nature, right? And if you learn a highly complicated non-linear model, then you may end up in overfitting problem. So this is the case of overfitting, and this is the case of underfitting, right? So underfitting means uh, training performance is low, and test performance or validation performance is also low, right? In overfitting, we are getting very good training accuracy, but very poor test accuracy, right? So in overfitting, training accuracy is good and validation accuracy is poor. In underfitting, both accuracy is poor. Both accuracies are poor, right? So training accuracy is also poor and test accuracy is also poor, right? So that case is called underfitting, right? So this is the case of underfitting and this is the case of overfitting, right? And this is the ideal case, right? So since here we are using a wrong model, we should use a non-linear model, but we are using a linear model. So if you calculate the training accuracy or if you calculate the training error, so here training errors are high, right? Or training accuracy is poor because the model is not able to fit the pattern present in the data, right? And here, as you can see, we have a non-linear pattern. So linear model cannot capture this non-linear pattern, right? So this is why here the training accuracy is poor. And since you are using wrong model, so if you use same model test time or future time, again you will get a very poor accuracy, right? So in this case, what we can say, training accuracy is poor and the test accuracy is also poor. So this is a case of underfitting. This is the case of overfitting because here if you calculate the training error or training accuracy, here you will get the 100% training accuracy, right? Because using this highly complicated non-linear model, you can fit each and every training data point, right? So since your model exactly passes through all data points, so therefore in this case you will get a 100% training accuracy. But clearly, if you use this model for the test data, you will not get a good accuracy, right? This model will perform poorly on the test data, right? So this is the case of overfitting, and this is the ideal case, right? Here, if you use this model, again, here training accuracy is not 100%, right? Because you will have some errors for this point, right? This point also we will have some error, right? And yes, so our model passes through this point. So for this particular point, we will not have any error. But yes, for this point, we will have some error, right? So here, the training accuracy is not 100%. So maybe you will get 99% accuracy or 98% accuracy. But if you use this model, the test accuracy also you will get in 96%, 97%, right? So test time it will perform good, right? So ideally we want this type of model, right? Here, if you use this model, 100% training accuracy you will get, but test time you may get 30% accuracy or 40% accuracy because we are not using the correct model, right? We are using a highly complicated model, right? And that highly complicated model try to learn each and every pattern present in the data. So this is why this model is learning this type of boundaries, right? Okay, any doubt in this example? Okay, so let's take another example. Let's say if you are learning a highly complicated model, and that model, let's say, may detect pattern like the fact that all countries in the training data with a W in their name have a life satisfaction greater than 7, right? Now, if you want to predict the life satisfaction for any country, now this particular pattern is not required, right? So this is a wrong pattern, right? Because what our model captures here using this data, that if country name having W in their name, then life expectation is greater than 7. So clearly this is a wrong pattern, right? So if model try to capture this pattern, then definitely we will suffer from overfitting problem, because test time, let's say when we have these Zimbabwe or let's say this country, then again it will give life satisfaction greater than 7, which is wrong, right? So this is why we want this type of model, right? We don't want underfitting, we don't want overfitting, right? Here in overfitting, we will get very good training accuracy, but test performance, test accuracy will be poor. Here both train and test will be poor, right? Yes. So regularization is a technique using which we can prevent overfitting. Now here regularization means we will regularize model parameters, right? We will put constraint over model parameters so that we can learn a simple model, right? Now this amount of regularization we can control using a hyperparameter that is called the regularization hyperparameter, right? So we have one hyperparameter. Hyperparameter is a parameter using which we can control regularization strain, right? So if you increase that parameter value, hyperparameter value, then regularization, the amount of regularization will increase. And if you decrease that parameter value, the amount of regularization will decrease, right? So we can control regularization or the strength of regularization using regularization hyperparameter. Okay, so let's take a linear model example. So linear model has two parameters, theta 0 and theta 1. So for example, y is equal to mx plus c. So y is equal to mx plus c is a line, equation of line, which is a linear model, right? So here you can see y is equal to mx plus c. So y is the output, m is the slope, and c is the intercept, right? Or you can think, so in this linear model, we are learning two parameters, slope parameter and intercept parameter. Right. So this value is c value. X-axis, y-axis. Yes. So tan theta is slope m, and this is the intercept value c, right? Now, if you change this slope value, orientation of this line will change, right? If you change c value, the shifting will change, right? If you choose here c is equal to 0, this line will pass through origin, right? So this line will pass through origin point 0, 0, it will pass through, right? If you choose c is equal to 0. If you change slope value, the orientation of line will change, right? Now let's say you are having a bunch of data points, right? Let's say you are having these types of data, and you want to fit a linear line, right? So if you change c value, if you change the orientation, you can fit a line, right? And let's say for other data set, let's say you are having these types of data points. So if you change c value, if you change theta value, now you can again pass a different line, right? So here, what are the learnable parameters? M and C. So these two are the learnable parameters. If we change these value, the model will change, right? So depending upon our data sets, we will learn optimal value of M and optimal value of C, right? So in this particular example, this slope here is the theta 1. So M is the theta 1, and the intercept C is the theta 0, right? So y is equal to theta 1 x plus theta 0, right? Yes. So since here we are learning two parameters, so this is why here I have written 2 degree of freedom, right? So we are having 2 degree of freedom because we are learning two parameter values, theta 0 and theta 1, right? Okay. So if we fix any one variable, so let's say if you fix c value, then we are reducing our possibilities, right? So for example, let's say if you put c is equal to 0, if you put c is equal to 0 means now this line has to pass through origin, and we can only change its orientation, right? Because if c is equal to 0, then this line will always pass through origin, and we can only change the orientation. Or let's say if you are fixing theta 1, let's say if theta 1 is 45, so now uh, the slope is fixed, this angle is 45-degree angle is fixed, and we can only change the c value, we can only change the other attributes, right? So if you fix any one value, or let's say if you're fixing this other value, then we are reducing our possibilities, so it will reflect our solution, right? Because let's say if we are having data points of type this, then here we need to estimate, we need to uh, obtain the correct value of slope and correct value of intercept, then only our model can pass through this type of data sets, right? This type of data points, right? Okay. So let's assume we want to fit a linear model over this type of data points. And here, as you can see, if you fit a linear model on using all data, then you will get a red line, right? So the red line we are getting when we use red linear line we are getting when we use when we train our model on complete data, right? And this blue line we will get when we use regularization method. We may use L1 regularization or L2 regularization, which means we are regularizing model parameters. We are regularizing our model, and after using regularization, we are getting this type of model. So as you can see, this model is better than the red model, red dotted model that we were getting without using regularization, right? Because if you see this red dotted model, this model is influenced by this particular point. So this point may be an outlier, right? And also this point, right? So this is why this red linear line is shifted. The orientation shifted so that this model can perform well on this particular data point, or let's say on this data points, right? But when you regularize your model, the effect of these points over model reduces, and this is why we are getting now a balanced model, right? Okay. So regularization forced the model to have a smaller slope, right? So as you can see here, since if we regularize our model, we are getting a smaller slope, right? And it fits a bit less on training data that the model was trained on, right? So, and actually this regularized model performs better on future data, right? So test time, the performance of this regularized model is better than the unregularized model, right? Okay. So now the question is, how do we choose the best model? So when finding the best model, we have to find the right balance between the fitting the data perfectly and keeping the model simple enough to ensure that it will generalize well, which means uh, what we want good training accuracy, and we also want good test accuracy, right? So fitting data perfectly means uh, good training accuracy, right? The training accuracy uh, has to be good, and keeping the model simple enough to ensure that it will generalize well means we want test accuracy, better test accuracy. So better training accuracy and better test accuracy, right? Underfitting I have already discussed, right? So underfitting, we will get poor training accuracy and poor test accuracy, right? So it occurs when we use two simple models, right? So for example, here in this example, uh, in this case, we are using a linear model to capture a non-linear pattern, right? So since we are using a very simple model, so in this case, underfitting will occur, right? Yes. So underfitting occurs when model is too simple, or when the model or algorithm does not fit data well enough. So when the model or algorithm does not fit the data well enough, in that case, we will get a poor training accuracy, right? Because model is not able to fit the training data, which means the training accuracy will be poor, right? So for example, here, if we use this particular model to fit our data, and as you can see, the model is not able to fit these points. So therefore, if you calculate the training accuracy will be poor, right? So in case of underfitting, the training accuracy will be poor, and at the same time, test accuracy or future performance will also be poor, right? Okay. So underfitting may occur if we use too simple model, or if a model is not able to fit the data well, or if feature that we are using if do not provide the enough information to make the prediction, then also we may suffer from underfitting problem, right? So what we can do if first point is the case of underfitting, if features do not provide enough information to make the good prediction, then what we will do?
You have to create new features.
Yes. So either we can create new features, or we can create more data, so that now we are able to make predictions using new data, right? Yes. Now, how can we solve the problem of underfitting? Again, if the simple model is the problem, then we can increase model complexity. We can improve. We can improve. We can use the sophisticated model to prevent the underfitting problem. So, for example, here in this particular case, we can increase model complexity. We can increase non-linear model to solve this underfitting problem, right? Yes. So we can select a more powerful model, right? We can feed better features to the training algorithm. So let's say if this first point is the problem of underfitting, then we can use new features that provide enough information now to make a good predictions, right? Or we can apply some constraint on the model. We can reduce the constraint on the model. So for example, we can reduce the regularization, right? Regularization hyperparameter, right? Because this regularization we are using to regularize our model, right? Now, if regularization strength is high, if we are using a high value for regularization hyperparameter, what it will do? It will regularize your model. And let's take one example. So let's say if you are using L1 regularization. So what L1 regularization will do? L1 regularization will make model parameters close to zero, right? But if you are using a very high value for regularization hyperparameter, what it will do? It will simply make all model parameters to close to zero, right? So here, let's say you are using this model theta 1 and theta 0, and you are using L1 regularization, and your regularization constant is very high. L1 regularization constant. So what that regularization will do? It will make theta 0, theta 1 nearly 0, right? So you will end up getting y is equal to 0. So what is y is equal to 0? Y is equal to 0 is nothing but the x-axis. So now, if you heavily regularize your model, you end up getting y is equal to 0, which is nothing but the x-axis. So now this x-axis cannot capture pattern present in the data, because to capture this pattern, you have to learn this model, right? Okay, so now how can we fix this problem? What we can do? We can reduce the regularization strength. We can relax our model, so that, and for that, what we can do? We can reduce the regularization hyperparameter value, right? Okay. So what we can do? We can reduce constraint on the model, and constraint means we can reduce the regularization hyperparameter, because overfitting and underfitting, if you are using regularization, then we have to use the correct value of regularization hyperparameter. If you do over regularization, if you do very high value for regularization hyperparameter, then it will penalize model parameters, and now you will suffer from underfitting problem, right? So if you are over regularizing your model, it will result in underfitting problem, right? So we should not apply a high value for regularization hyperparameter or a very low value of regularization, and we should choose this regularization hyperparameter optimally, right? Because let's say if you are using a very low value for regularization hyperparameter, so if regularization hyperparameter value is too low, in that case it will act like you are not regularizing your model at all, right? If regularization is hyperparameter is high, which means you are over regularizing your model. In that case, underfitting may be there, can be there, right? So we have to choose this regularization hyperparameter in such a way it should not result in over regularization, or it should not result in underfitting, right? We can feed better features to our model if model is suffering from underfitting problem, or we can increase model complexity to prevent underfitting problem, right? Okay, so next session we will continue from this slide, and we will train model using our process data, right?
Dr. Praveen, you said about
Yes, yes.
regularization. How to do the regularization, that you didn't mention. You said
Yes, yes,
some hyperparameter, right?
yes, yes. So regularization part I will cover later.
Oh.
Any other doubt? Okay. Okay, so thank you for joining. I'm closing this meeting.
We
Thank
share
you,
the
sir.
today's link. Hello?
Yes, slide.
Slides and also recording link.
Okay.
Yeah, thank you.
Thank you, sir.